Wong. So Dr. Raymond Wong is an associate professor in the Department of Statistics at Texas A&M University. He got a BA and an MA in statistics from the Chinese University of Hong Kong and a PhD in statistics from UC Davis. So Dr. Wong has made important contributions in functional data analysis, causal inference, and statistical learning more broadly. So thanks for being here, Raymond. We look forward to your talk.
Thanks for the invitation. Thanks for the introductions. Thanks, Gary, for the invitations. And thanks all of you for coming and joining through Zoom also. So I'm glad to have a chance to share my research with all of you. So I'm going to talk about reinforcement learning, our recent work on reinforcement learning. Indeed, this is actually my first work in this area. So I'm still learning. So please bear with me if you see anything unclear. I will try my best to answer your questions. So, okay. Let's begin. Okay, so reinforcement learning is characterized by an agent continuously interacting with an environment. So, and interactions consist of three major components: observations, actions, and rewards. So, at a particular interactions, an agent will try to make observations of the environment, which is usually mathematically summarized as state variables. And then according to a strategy, which is also known as policy, the agent will try to make take an action according to the observations. Then the environment provides feedbacks in terms of rewards. So in reinforcement learning, such interactions happens in a sequential manner, which lead to a sequential decision-making problem. So the goal of reinforcement learning is to use data to learn how to choose the actions to maximize rewards. So, of course, reinforcement learning is a hot topic. You can find many applications of reinforcement learning in many different areas, such as in autonomous driving and also mobile health. So, and there are two major settings for reinforcement learning, online and offline. In online setting, the agent can interact with the environment to collect data, while in the offline setting, the agent cannot interact with the environment. So, but the agent is given offline data set to learn the policy. So, and this offline data set might be collected based on a different strategy, and this usually lead to distributional mismatch or distributional shift, which constitute a major challenge of the offline setting. So, and usually the offline setting is regarded as a more challenging setting than the online setting. And in this talk, we're going to focus on offline setting. The more specific problems that I'm going to talk about is policy evaluation. In the next few slides, I'm going to introduce the problems and also the setup. So now let's consider a trajectory of interactions. And again, an interaction consists of three major components: states here, action, and reward. So in this work, we're going to allow like general state space. That means the state variable can be continuous. While for simplicity, I'm going to restrict the action space to be finite. But there's no fundamental difficulty to extend our work to continuous action space. So it just makes my life easier to describe. And following the practice of reinforcement learning, I'm going to make Markovian and stationary assumptions. So more specifically, given the current state and action pair, the future states are independent of the history. And we have a similar type of assumption for reward, but only on expectation. So here, the transition kernel P and the reward function R are assumed to be time invariant. To generate the trajectory, we need a policy. And I'm going to focus on time invariant Markovian policy, which is also known as a stationary policy. So the policy is essentially just a map from a state to a probability mass function over action. So you can also regard this as a conditional probability mass function. So to recap, at a particular decision point, we have the state variable st, and the agent, according to a policy, will choose an action at, and based on s and a, the environment will produce reward and also the next state. And the policy will be evaluated based on a quantity called policy value, which is defined in this way. So if you look at this definition, you can see that it is essentially just an expectations of the discounted sum of rewards. Okay, we scale it a bit, okay, here, but that's not very important. Okay, so here gamma is the discounting factor. This can control the trade-off between the emphasis on the future and the immediate rewards. If gamma is closer to 1, then the value will have more emphasis on the future rewards. So here the expectation is taken with respect to a distribution induced by the target policy pi and also an initial reference distribution G. So you design how to evaluate the policy. So you choose G. So that's why G is low. Okay. So if you look at the definition, you also see that the sum is taken over infinite time point. This is what we refer to as infinite horizon. And as an important and related quantity is the state actions value function. So which is also known as the Q functions in the domain. So this Q function is essentially just a conditional expectations of the discounted sum of reward given the current state and action. So of course, with the Q functions, you will be able to recover the value quite easily by taking a further expectations over the state and actions, initial state and actions. And of course, you can rescale it by a bit, okay, to get the value. So this function will show up in the later part of the talk. So that's why I introduced it. So as I said, I'm going to focus on offline setting. So we are not allowed to interact with the agent. So instead, we are provided with a pre-collected training data set, which I assume to consist of an IID finite horizon trajectory. And this trajectory are collected based on a fixed stationary policy B and an initial distribution G0. So this B and G0 might be unknown. And for the technique that I'm going to introduce, we don't need to know these two quantities. So this policy B is usually called the behavior policy. When the behavior policy is different from the target policy, your target policy, then the corresponding policy evaluation problem is called off-policy evaluation problem, OPE problem. So and for simplicity, I'm going to use this notation E to represent expectation taken with respect to a data generating mechanism. Okay, that means taken with respect, that means the distribution induced by the behavior policy. So in off-policy setting, the distributions of the trajectory in our data is different from the target policy induced distributions. And this creates a distribution shift, okay? And that causes some troubles. So, moreover, even if we are on the, even if we have the on-policy setting and the initial distributions are the same, we are not able to directly use the average of the discounted sum of rewards in the data to estimate the policy value because we only have finite horizon trajectories, while the quantity that we are interested in is infinite horizon. So there are many different OPE methods. One big class of OPE method is called model-based method. This relies on directly estimating the dynamics. So and the other class is model-free methods, which just try not to do it. Okay, try not to estimate the dynamics. And we're going to focus on model-free methods. There are roughly three major categories of model-free methods. The first one is direct methods, which is based on estimation of the Q function. So as I said, right, if you know the Q function, you can then you can compute the value. Okay. So this Q functions is characterized by the celebrated Bellman equation. So which is listed here. This Bellman equation provides a moment restrictions, okay, of the Q functions. Many methods are trying to base on this moment restriction to develop an estimation for the Q. And the second class of method is called marginal importance sampling methods. To see how it works, essentially you can rewrite the value in this form. Here you can see we have a probability ratio function. Okay, the explicit definitions is not very important. Okay, for the rest of the talk. Okay, but of course it's defined this way. So I'm going to just call this omega. Okay, the weight function. So, and if we know the weight function, well, then this actually gives us an unbiased estimator. The weighted sum is an unbiased estimator for the value. So another characterization, so instead of using these characterizations, later I will also use another characterization of the weight functions. So here I have a set of infinite number of moment restrictions, moment characterizations. So this also characterize the weight. This also identify the weight. So here so you can see for each f we have a moment restrictions, and we lead this to hold for many different f. Okay, so I'll come back to this later. So, and the last category is what we call double robust estimator. So this essentially try to combine the direct methods and also the weighted methods. So for those of you who are familiar with FA treatment effect estimations, right? So the direct methods is essentially like an outcome regression model estimations. So Q is like Q actually has similar role of that. Okay. So, and here we have the weighting. Okay. So they try to so this class of method try to combine both to create the robust estimator. So our proposal fall into the second category, weighting method. So a generic form of weighted estimator is this. Here, omega are some weights estimated from the data. So, well, a simple strategy might be try to estimate the weight, okay, the probability ratio function, the numerator, the denominator directly, and then evaluate it at the observed state action pairs. Then we have the weight. So this is very similar to IPW, inverse probability weighting, commonly adopted in ATE estimation problem. So, and of course, like we know that from ATE problem that the IPW estimator, IPW weighted estimator is not very stable due to inversions of weight of probability. An alternative approach is covariate balancing approach. So the idea is to find stable weights that achieve covariate balance. So in a simple way, it is trying to maintain an empirical versions of the moment restrictions. Okay, so now let's try. We want to actually adopt this covariate balancing idea to deal with the policy evaluations in the reinforcement learning setting. So the first thing is about moment conditions, moment restrictions, and in fact, I already list the moment restrictions here. Okay. So you can just take these moment restrictions, and of course, this has an expectation here. We don't have it, so you replace it by an FH. This is like empirical version. Okay, and we require the original moment condition to hold for infinite number of functions, which is difficult. So in practice, we only need this to hold for a finite dimensional subclass. Okay, function subclass, a function class. So B1 up to BK, so this class is generated by some K basis functions. So in theory, you want K to grow, okay, so to avoid any bias. So, and then you can try to take some proposal of covariate balancing approach, right? And then try to use this new moment restrictions. And this is what we do here. So we take a proposal from Wong and Supersarita, and then essentially just replace their moment conditions used for ATE problems by the moment restriction that I just mentioned. Okay, very simple. So although I have lots of notation here. Okay, so here in this covariate balancing estimator, the moment restriction, the empirical moment restriction does not have to be exactly hold. So they allow some wiggle room. So this delta K control the imbalance. So here H is chosen as non-negative, strictly convex, and continuous differentiable functions. This H is this term here is essentially try to actually regularize the weight so that the weights do not vary a lot. Okay, so so as to produce stable weight. So and of course, given this this optimization will generate the weights, and then you can form the weighted estimator. Now to understand this estimator, you can try to look at the error decompositions. And this is where things get interesting. So when you look, so we can decompose the error of the weighted estimator into three components. So the first two lines correspond to the first component, and then here, second one, this is the third one. Okay, if you look at the first two lines, okay, you can see it's very similar to these restrictions, okay, which we actually directly control in the optimization, right? So the only thing that difference is that I do not have a B here. Instead, I have a Q. Okay. So as long as the Q functions well approximated by the basis functions. So and also you kind of like choose this imbalance, that means delta K carefully, you can control this guy, control the first error. Okay. So the second one is a little bit more interesting, but not too difficult. And if you have some nice condition. Well, if you look at the weight, just look at here. So there's no reward in use in constructing the balancing this weight, right? So we only use state action pairs. Only state and action shows up here. Okay. So while this epsilon is the difference between the reward and the conditional expectation of the reward. It is like an error. It is like an error in the regression models of the reward. Okay. So if you conditional on all these state actions, then the weights become fixed in this conditional world. And then this epsilon still random because this is a randomness that we see here, right? So if you have some nice conditional independency assumptions on epsilon, so you can this term still demonstrate some concentrations. So this term might be okay. So the last term is where the difficulty comes in, because you look at this here, you can see that this is also a function of state action pairs. So in other words, if I have to understand whether this term demonstrates some concentrations or whether I can control it, I have to understand the complicated dependency, which is very hard indeed. So it's unclear to us like how to control this term. And in fact, when we dig deeper, we find out that there is unpleasant issues that occur with this estimator. So let's take a look at this this issue. Okay. So if you look at the dual form of the optimization, okay, this is a dual form, okay, you can also use the solution of the dual optimization to represent the primal, okay, which is the weight, okay. So here, this rho prime is just monotone functions, okay. You don't worry about this, it's just a monotone transformation, okay. And then this lambda star is the solution of this problem, which is like a coefficient. And this psi k is like a basis, it's like basis functions. It's more or less like you are trying to use this as a basis function to model these weight functions. Okay. However, the issue is that you can see this is a function of SAS, right? And while the true weight function is just a function of S and A. So if you go back, right, the definitions, it's only S and A, right? So now we have an extra dimensions, and this is what we call an expanded dimension issues. So this does not align well with our true weight functions, and this could cause issue. So when we actually go on and investigate this, what we find is that what we can prove is that there exists some true weight function that the solution form cannot model under a finite state, finite action settings. Okay. In other words, there are some model. In other words, if you try to use this estimator, there are some model mystifications implicitly induced here. So, well, of course, like you may find you may sound surprising, right? Expanded dimensions are supposed to be more flexible. Okay, why would that be? Why would now being more restrictive? So because this psi k is not just some it's not some light basis. It's actually a transformational basis. There are some reductions that implicitly be induced here. Okay, so well, anyway, like this estimate is not good. Okay, so we're trying to actually tackle this issue. So we go back to the moment conditions and we find out that the issue shows up here, right? Mostly because like we have this ST+1 here. This is the major reason why this extra dimension shows up. So the idea is very simple. We try to rewrite the moment condition by stuff in a condition expectations. Okay, by double expectation formula, these two are exactly the same. I didn't actually change the problem. okay? But this conditional expectation is just a function of STAT, right? Because ST plus 1 is being average out, okay, somehow. So instead, okay. So this guy, actually, we have given a notation for this before. Okay, I didn't talk about that. I call it G star, okay? So which is actually exactly this guy, okay? So this is just notation, okay? Didn't actually do anything tricky here. So now then our goal is to find ways to control this balance instead of the original one. However, this G star is unknown. We don't know that. It's conditional expectations, okay? So, but it's conditional expectations, so it's just a regression problems, right? Yeah, you can also call it projection problems, okay? So, and then in this work, we try to just estimate it, okay? So by along parametric regressions, more precisely, a kernel-rich regressions. The details are not very important, okay? So basically, I perform regressions to estimate them. But for something that you have to pay attention to is that you look at here, the response has a BK, has the basis functions. In other words, you have to perform the regression for each single basis. Okay. So essentially, if you have K basis, you have to perform the regression K times. Okay. So, and after that, you have the G hat, then you can modify the estimator. Okay. And this is our proposal. So, and of course, and I will call this omega hat, the corresponding weight as omega hat, and this is the corresponding weight estimator. So we can then go through the same exercise, okay, to look at the dual, start to check whether the expanded dimension issue is still there. So, and of course, the expanded dimension issue go away, okay, so this is the corresponding form. So you can see that the working basis, okay, for our model is LK hat. Okay, what is LK hat? It's defined here. It's BK minus gamma G hat. And well, it's a kernel-rich regressions. Okay, so and actually in our theory, we actually show that it converge. Not only it converge for each K, it converge uniformly for all K. Okay, so that's why it's going to be okay. Okay, that you use all of them. Okay, simultaneous here. So so essentially, you can think of, okay, this is just an estimations, right, of the working basis. And this is actually the true working basis, okay, the true working basis that we have. But the same question comes up. Well, I can choose BK very carefully to model what I want to model. However, this LK, which is the actual basis that used to model the weight function, is the transformations of a BK. So I would not know whether there would be any interesting reductions of the expression power of the basis, right? So I will know, I don't even know LK, what it is. Okay, exactly, right? It's go through a condition expectations. Okay, so you may have a concern that actually, well, you don't know what LK is, and you don't know what LK is trying to model, and you don't actually know what this estimator is trying to, what is the working model for omega, okay? So we're going to come back to this problem later. In fact, this also shows up in our asymptotics. And more than that, it is actually to a bigger study. So, but let's go on first, okay? So the computation is simple. It's just two steps. So the first step, you estimate G hat, okay, by the kernel-rich regression, and then you find the weight. And the weight is defined by a convex optimization. So there are many software that can be used for that. So now let's take a look at the statistical convergence results. Okay, we're going to look at 3 different quantities. So approximate projections, the balancing weights, the value estimator. Okay, so here I need some more notations in order to, before I go on. So this represents the empirical norm. This represents the L2 norm. Okay, and then we have D, which is dimension of the vector. And I guess many of you, especially the younger generation, know the internet slang, TLDR. Okay, too long, didn't read. Okay, so in the following, okay, I will have lots of I will have to discuss the theorem statement, right? But I have lots of assumptions that I do not have time or space to display. Okay, I create my own slang. Okay, TLDW, too long didn't write. I'm going to use it to hide the condition that I don't want to talk about. Okay, so okay, so yeah, so like this is the result for the approximate projections. Okay, you don't have to actually spend too much of your energy looking at the statement. Okay, this is kind of like middle result. Okay, I'm going to tell you a bit. I'm going to tell you the important part. Okay, so essentially this result shows uniform convergency because it's uniform. It's so uniform convergence of G hat over any linear combinations of the basis functions. Okay, so that's actually what we did, and also. Another important features for this is that this scale with both n or nt. So you can have convergency or even under fixed n settings. So just to remind you, n is a number of trajectories, t is a number of decision points. Okay, so this will be very useful actually for our later applications. And this is we're going to have a mobile health applications. Okay, so in that case, we have very small number of subjects, but we have a long trajectories. Okay, so this as important will still be somehow relevant. Okay, so to that scenario. So and then you can go on and then suppose some nice conditions. So we can have convergency of the weight function. So in both the empirical L2 and also the L2 norm. So again, like this result also holds as long as n or t goes to infinity. Okay, so you can have a small n, large t regime. You can have a large t, small n regime, and so on. Okay, so this result still be relevant. So to the best of our knowledge, this is the first consistent result of ratio function that can scale with both n and t. So okay, so far so good, because I hide all the condition. Okay, and I'm depending on you to trust me that I'm doing a good job. Okay, in selecting condition to display. So in fact, here there's one crucial condition that I didn't display. I should actually display. Okay, now let's look at this. Okay, so this is like a fuller version of the one that I showed in the previous slide. So this term shows up. This is a minimum eigenvalue of the expected grand matrix of LK. If you recall, like we have a questions about LK, this transform basis, we don't know what it's doing. Okay, so and actually it shows up here. Okay, so in fact, like this minimum eigenvalue is also directly related to the convergency rate. Okay, that we see here. So of course, like if this eigenvalue is minimum eigenvalue is 0, our result do not even indicate convergency. Okay, so this is crucial. Okay, so for the rest of the theoretical result, you can pay more attention on the non-parametric settings. Okay, so in the non-parametric setting, then you will want k to grow, right? So in that case, we will then be interested in the decay rate of psi k. Okay, how fast it decay? Okay, so and that's going to be important. So and if you okay, let's just keep psi k and go on, right? Then you can derive the convergence. Then we can derive the convergency of the value estimator. So this is the convergency rate. Okay, so you can see k is here, right? Usually, if you have experience with long parametric regression, especially with seal space, you know that, right? A lot of time we try to actually strike a balance, right? To choose optimal model of k, like the balance out to get a fast order. So if you want to do that here, you need to know psi k, okay, to do that. So again, I'm going to actually discuss psi k a little bit later. So suppose psi k is strictly bounded away from 0. That means there's a positive constant. Okay, that psi k can never go below to that, no matter how large k is. Okay, then we can even show the asymptotic normality of the value. Okay, of the estimated value. So and if t is fixed, so again, like this result holds for either n or t goes to infinity. So this is still relevant for small n, large t settings. Okay, so if t is fixed, we can actually show that like this estimator achieve a semi-parametric efficiency bound, and there are only 2 power works that when we write this paper, there are only 2 power works that we know have established the convergency rates. For non-parametric models, yeah, that shows that's under the scaling of both n and t. So in our result, our analysis actually will let some of the restrictive conditions that they have in their analysis. So now let's get back to the most important, the important quantity, the minimum eigenvalue. Okay, so well, to discuss this quantity, I will need a little bit more notations. I know I've introduced a lot of notation. Okay, so but I'm going to go on to still introduce more. Okay, so here we have this p pi, which is just an operator, right? Just the conditional expectation, just represent conditional expectations. Okay, and then we have I that represent identity operator. And then I'm going to use this E bar to represent the FH visitation distributions. Okay, it's FH, it's just FH across all time point. Okay. So now, with these operator notations, you can express LK in terms of this form. Okay, this BK is the basis function that you choose. You can choose something that's nice, right? And LK is the working basis, right? That actually used to model that eventually used to model the weight. So, and this is something in between. Okay, so the I minus gamma p pi is the operator. Okay, that perform the transformations. So in the following, I'm going to focus on instead of focusing directly on psi k, the eigenvalue, I'm going to focus on the minimum eigenvalue of this operator, because in this case, then my study will be independent of the basis that you choose. You can choose any BK, okay? So because this is the sum, you can choose any nice BK such that the behavior is nice, but this guy might be actually doing some bad job, right? Trying to screw things up, maybe. So we try to understand this, okay? So and this epsilon represent the minimum eigenvalue, okay? So and of course, like if you know epsilon, then you can actually lower bound psi k by epsilon and also the minimum eigenvalue for bk. Bk is something that you choose, okay? So you're going to choose this nicely, okay? This condition, so the boundedness of this aligns with typical non-parametric regressions, okay? So so to give you a little bit more motivation to study epsilon, so I will also let you know that like this epsilon is directly related to the difficulty of the Q function estimation. So far you can see like this epsilon shows up in the minimum eigenvalue, right? For our problem, right? We develop a weighting approach, okay, which is the second category, in the second category of the model free methods. But this quantity also relate to the fundamental difficulty of the direct methods, okay, or more precisely related to the difficulty of the Q function estimation. So this is indeed a very important quantity, okay. To see this, I provide some intuitions, okay, here. So if you recall, I mentioned that like we use the Bellman equation, right, for estimations of Q. So with our operator notation, you can actually rewrite the Bellman equation in this form. And now you see that this operator comes up again, I minus gamma p pi, okay? And we have observations, RT, ST, AT, and of course, the conditional expectation, which is the reward function, okay, can be estimated by a regression problems, right? By regression. So in other words, we can estimate the left-hand side from the data while we're interested in Q. So this operator stand in our way, okay? So, and if there is any signal of Q that's completely canceled or removed by the operator, we are not able to actually recover that based on our knowledge of the reward function R. So that's why it's important. And that is also the reason why like you want to look at like the minimum eigenvalue of this operator. Okay. So, and what those are heuristic. In our paper, we actually show this more rigorously by deriving a minimax lower bound for the estimation of Q function. So, and our result actually indicate that if this epsilon is not strictly lower bounded, the minimax lower bound will indicate a slower rate. Actually, you cannot, it will slow your convergence. So that's why this is directly related to the fundamental difficulty of Q function estimation. So now I have done enough advertisement, okay? So definitely, I'm going to actually present some results on that, okay? So this is part of the reason why I spend so much time advertising it, right? So in this work, we provide a new characterizations of epsilon, okay? So we look at a quantity called psi, okay? And epsilon and psi are related in this way. So psi is defined in this way, okay? You can look at here, you will see that actually in the definition of psi, there's no operator I minus gamma p pi here. So we don't have to look at the transitions, okay? Instead, this involves the conditional discounted visitation probability. So this, of course, you might think that, okay, this is still in alien language, right? So why would that be nice, okay? So this has something to do with that, like a lot of times when we try to investigate conditions, we are interested in something like overlapping conditions. So the overlapping conditions directly related to the FH visitation probability in the data, and also the visitation probability, right? And also the discounted visitation probability that's induced by your policy. So this is more directly for that probability. So that's why it's easier for you to try to create condition or understand this condition. Okay, so that's why this is important. I think that's why we think it is important. So, but that's actually that's characterizations. Okay, so that's very precise characterizations. And so as a demonstration, we also use that condition to create some sufficient conditions. Okay, so for the lower boundaries. So this is the sufficient condition that this is an example, okay, of sufficient conditions. So the first condition essentially indicate that we have the FH visitation probability is lower bounded by a constant, okay. So this is a strong condition, but this is also reasonable conditions, because this ensure that like you can evaluate ensure like a good overlapping conditions, okay, because like visitation probability in the data is strictly lower bounded. So and then we have another condition which is not very crucial. It's just about the upper bound of the transition probability. Okay, so with this sufficient condition, we can definitely show that we have a strict lower boundaries. Okay, for epsilon, and also the minimum eigenvalue that we're interested in. Okay, so here I have some remark. So in existing literatures, some paper also encounter this issue. So for those papers essentially try to show the minimum eigenvalue is uniformly bounded away by making an assumption that gamma has to be small enough. Gamma is the discounting factor. Okay, so in our result, we don't have to make such assumptions. Okay, so in fact, like sometimes we are actually interested in large gamma, especially if you are more focused on the long-term reward. Okay, so this is actually a very big restrictions. So here's another remark. So at the same time, there is a parallel work which also focus on this, on understanding minimum eigenvalue. So this work provides sufficient conditions. This is actually comparable with our sufficient conditions. Also makes certain form of like bounded assumptions. Okay, similar, but our result is sharper in terms of dependency. And more importantly, our major characterization result is not just a sufficient condition, it's the if and only if conditions. Okay, sufficient and necessary conditions. Okay, so and that condition do not directly require any boundless conditions on the FH visitation and transition probabilities. In other words, for future development, if you are interested in like some more interesting overlapping conditions, so our characterization result would allow you to be able to try to derive other form of conditions. Okay, so which might be useful. So we have some numerical results. So in these numerical results, so we follow like some recent papers, okay, to formulate the simulation settings. So and we focus on 4 target policies. We have like different combinations of N and T. So we compare a bunch of methods, relearning. This is the JASA paper, and SAFE, which is the recent JRSP paper work on. So, and then some common method in the domain FQE, important sampling, mean mass weight, double robust. Okay, we compare a bunch of estimator. So Here are the results. So our methods is usually among the best two in terms of the performance, in terms of MSE. So with the asymptotic normality, we are able to also create a confidence interval. So there are three methods which has confidence interval: our method, the relearning, also the safe estimator. So we found that the coverage is usually slightly lower. Our method is usually slightly lower than the nominal coverage. Okay, so we recommend to kind of like widen the interval by maybe 1.2. So and these are the corresponding length, average length of the interval. So you can see, so our method actually perform pretty stably. So here I have to make a remark: safe, for this method safe, in their calculation of the confidence interval, it involves an inversion of a matrix. Sometimes this matrix is numerical singular. So that's why the confidence interval can be very wide because of that numerical issue. So, and we also try some game environments. This is Atari game. So based on the OpenAI gym environment. So we only look at the couple example. So the idea is to actually kind of like derive a policy, right? So that the pole do not fall. Okay. So we have some result here. Okay. So but similar conclusions. So this is the real data application. So we apply our method to a continuous glucose monitoring data collected by Ohio University. So this data set contains approximately 8 weeks of records of CGM blood glucose levels, insulin dosages, and some self-reported life events of 6 subjects. So N is 6, okay, very small, okay, but we have longer trajectories. So, and we follow a recent work and derive 3 state variables. The first state variables is related to the glucose level, and the second state variable is related to the carbohydrate intake, while the last one is related to basal rate. Okay, so and we have a binarized action, which is based on the amount of insulin injected. So and I'm not expert in this area, so essentially we follow we follow the literature. Okay, and to use this IGC as the immediate reward. So and we look at 6 reference distributions, and they are just Paul mass at the initial state of a subject. We have 6 subjects. Okay. So, and we evaluate 3 methods, okay, that has a confidence interval. So, and we look at like 2 policies: always treat and never treat policy. And some prior literature shows that the always treat policies is closer to the optimal policy. So we expect the value to be larger. Okay. And here are the results. And basically all methods, the point estimate of all methods aligns with these expectations. And here you can see for relearning, the difference are smaller, okay, and safe produce a very similar point estimates as our method. So and we also see this stability issue of the confidence interval due to the inversions of a numerically singular matrix for the safe method. So that's so that's pretty much all I have. Here is our work. If you're interested in that, you can take a look. Okay. So and I have 2 collaborators on this work. So Wong from UT Dallas, Zhenning Qi from George Washington University. Jia was my previous students who just graduated, just joined UT Dallas, and Zhenning is an assistant professor at George Washington University. So I want to also acknowledge support from NSF and also the Texas A&M High Performance Research Computing. And that's all for my talk. I'm happy to take any questions. Thank you.
Any questions?
Yeah.
So basically, the camel will assume this line of structure that where that's the action will only states.
State and action. Yeah, they are related. Yeah, they are related, yeah. I think so. So if you look at the relearning paper, this is so you will see the causal, you will see the potential outcome framework. So they actually use the potential outcome framework to talk about all this. So yeah, so essentially the idea is that like you can think of you can have a potential trajectory that based on the different actions that you take. So yeah, that's some people use that framework. Yeah, no problem. Yeah.
We consider this loss, which is the infinite horizon.
Yeah.
Now,
Yeah.
wonder if you there finite horizon loss, what would be the major?
Yeah, like first of all, that's not loss, but that's the value. The higher the better. Okay. So but yeah, like there are finite horizon settings and also infinite horizon settings. So for finite horizon settings, sometimes you might not have the discounting factor, so you just sum it over. So usually people are interested in slightly different settings. Well, if they focus on finite horizon, they might not require stationary assumptions. So they might allow like things change across time point. So yeah, but both settings are common in the area. Yeah.
There might be a restriction on it.
So at least from my experience, in finite horizon, sometimes people are also interested in dropping the stationary assumption, dropping some stationary assumptions. So essentially, like different time point, you might have like different things. So in other words, saying in that case, then you have to estimate more. Okay, but it's finite horizon. So T is supposed to be fixed, so it's still doable. For infinite horizon, you have a bit more trouble for that, yeah. So especially if you only have finite trajectories, finite horizon trajectories, you are not able to deal with something that you cannot see. So yeah, so that's why like some form of stationary assumptions will be needed. So they are different settings, and both settings are popular in reinforcement learning. Yeah, no problem.
Yeah, that's here.
Yeah.
I guess you have a lot of assumptions, so you basically can just add this to one and then run PT.
That's right. That's right. I also have according assumption. Yeah. Yeah.
But you can also have just one two ideas.
Yeah. That's right. That's right. That's why T can be fixed as 2 and then N goes to.
So I guess we just have you try, let's say this first starter and then we
Yeah.
and
Sorry, can you break down?
I guess that's so
Yeah, we didn't try that. But yeah, but yes, in fact, like if you look at machine learning literatures, so a lot of times their setting is that they have IID copy of single transitions. So this is how they do their. It's a very common setting when they do the theory. So so I'm not. So this is somehow also related to what you asked, but we never really try to do that numerically. Yeah, but that's doable because you can see like all the informations are just hidden in a single transitions, right? So yeah.
Any other questions? So in practical settings, you might assume that some of these things are observed with error. So do people look at assuming an error model, some of those quantities like the rewards?
It's going to be difficult. Like then sometimes you might have something similar to unmeasured confounders. You could have something like this. So if there are some might be measurement errors for some terms. So reward has error. That's okay. But I'm guessing. So we have stochastic policy. So the policy do not there's some sort of chaoticity there, but you still have to observe it like correctly. Yeah, but with some of these measure with unconfined with measure errors, I believe that some of this will fall into the category of unmeasured confounder. Yeah, you have troubles with that.
Okay, then let's thank Raymond again.
Thank you. Thanks.